Functions. The objectives in our lesson is that we will determine whether a relation represents a function, we'll find function values, determine whether a function is one-to-one, and use the vertical line test to identify functions. An ordered pair contains elements from two sets. The x elements form the input and the y elements form the output. A relation is a set of those ordered pairs. The input set, all of the x values, are the domain of the relation, and the output set, the y values, are the range of the relation. A function f is a relation that assigns a single value in the range to each value in the domain. In other words, no x values are used more than once. We say the output is a function of the input. The input values, or the independent variables, make up the domain. The output values, or dependent variables, make up the range. A quick way to remember this is to say that a function is a relation where every x has exactly one y. Our notation for functions is the following, where x is the input and f of x is the output. So f of x equals y. F of x is in place of y. So our linear function was written this way before. Now you'll see them like this. F of x equals 2/3 x plus 2. There are many reasons for function notation, but it is a really nice, efficient way to show inputs and outputs and to be able to route you to different formulas as you're working through different problems. So we'll get used to that notation as we work through functions. Now, functions can be represented in the form of schematic diagrams, tables, equations, and graphs. So let's look at how to work with each of these forms. Determine if the following relations are functions. Here I have this schematic diagram of inputs and outputs. I see this x is getting routed to exactly one y, or this input is getting routed to exactly one y. This input is getting routed to exactly one output. So this is a function. This input is going to exactly one output. Same here, same here. This is again a function. Here, this input is getting routed to one output. This input, however, is going to two different outputs. So this is not a function. A real life example of something that works like a function would be maybe a soda machine. So you see a soda machine, you put your quarter in and you press the root beer button, and you expect that a root beer is going to be the output of the machine. Now, if you put the money in and press the root beer button and a root beer comes out, and your friend puts the money in, presses the root beer button, and a lemon lime soda comes out, we'd say that machine is not working right. It is not functioning properly. It is not a function. You cannot have the same input of pressing the root beer button and get the root beer out or get the lemon lime soda out. Okay, here we have roster notation. Roster notation of some relations. Here I see that 1 is going to 2. 2 as an input is going to an output of 4. 3 as an input is going to an output of 6. And that means this is a function. Here, this input goes to one output. But here we have the same input going to a different output. Okay, this is a case where we got root beer and a lemon lime soda and the same button. We already know, we don't even have to look at any more points. This is not a function. Select all the tables that represent y as a function of x. So here we go. 4 goes to 1. 7 goes to 9. But 7 also is going to 2. This is not going to be a function. Here 4 is going to 1. 7 is going to 9. And 15 is going to 2. We can safely say that's a function. And here 4 is going to 1, 7 is going to 9, and 11 is going to 9. Every x is going to exactly 1 y. That is a function then. Right, based on this table below, we want to look at the set of inputs and the set of outputs. Remember that this means y. And we're being asked to evaluate f of 5. So what is f of 5? Well, you see, normally they're telling you f of x. So this is their way of telling you that they're letting x be 5. So let's find an x value of 5 in the table. An x value of 5 is right there. And apparently when we put that into the f function, then out comes 45. So we have f of 5 equals 45. You see the input of x, and f of x, which is y, equals the 45. On this part, they're asking for us to solve this f of x equals 7. In other words, they want to know where the y is 7, what is x? What is x? So let's find an f of x value of 7. There we go. And that is going to be 2. So f of 2 equals 7. That must mean that x equals 2. We've solved it to find the x that makes that function have an output of 7. Now there is no other 7 as an output here, so that is the only solution. You will want to check that. Sometimes you can have more than one input that gives you the same output, and that's perfectly fine with a function. Functions in the form of graphs. Here we have a graph of a nice function, and we can see the input and output in the table. Okay, so you see -2, 4, -2, 4, -1, 1, -1, 1, 0, 0, 1, 1, 2, 4. Every x goes to exactly 1 y. You don't see any repeated x values. Now, as we mentioned before, we have repeated y values, and that's okay. In this function, we put in a -2 when we get out a 4, and we can put in a 2 and also get a 4. So recall that functions are sets of ordered pairs where each input value has exactly one output value, or again, every x has exactly one y. Graphs are collections of ordered pairs, but not all graphs are functions. To determine whether a graph represents a function, we use the vertical line test. If we can draw any vertical line that intersects a graph more than once, then the graph does not represent a function. Now, why would this work? Let's look at the graphs below. If we want to draw a vertical line through here, And you can do this with a rolling pencil. Roll your pencil from left to right. It doesn't matter where we move the pencil, it's only ever going to touch the graph one point at a time. This is a function. Let's try this. We have our graph. We're going to take our pencil and run it through from left to right, and it's hitting more than one point at a time. Okay, we can see that here and here. So this is not a function based on the vertical line test. Okay, and let's try this again. We've got our line, and we're going to pull it through that graph, and we can see it's hitting more than one place at a time. So again, this is not a function, not a function. Now the question is, why does this work? Well, let's go ahead and give these points here. Let's go ahead and give these points some labels. We can call this one maybe 5, so this would be 5, 3, and this would be 5, negative 3. So you can see one value of x goes to two different values of y. Over here, the same thing. Maybe this is 4, and this would be 4, 3, and this would be 4, negative 3. Okay, we have a single value of x that ends up going to two different y values. So this one is not a function. And the reason the vertical line test works is that you're using the same x value and hitting those y values. Let's look at how to evaluate by given a graph. Here we're asked to evaluate f of 2. Again, it usually says f of x, so they're telling us here that x is 2 where they want you to find the value. So find the x value of 2 and either move down or up to be able to get onto the graph. Here we have to move up. There's the point 2, 1. So I know that f of 2 equals 1. When I put in an x of 2, I get out a y of 1. Now we're asked to solve f of x equals 4. Remember, f of x means y. So they want us to find where the y equals 4 and what x gives you that value. So here is where my f of x is 4, and I can see there are a couple of places where that happens. That point is negative 1, 4, but we also have 3, 4. So we get two solutions here, x equals negative 1 and x equals 3. That's the solutions to f of x equals 4. Now we can have functions in the form of equations. How to evaluate a function given its formula: we replace the input variable in the formula with the value provided for x and then calculate. When evaluating functions, it's handy to wrap the input variable in parentheses before making the substitution. For example, given f of x equals 7x plus 1, some people would write f of parentheses equals 7 times parentheses plus 1. It reinforces that this rule, which is what a function is, says 7 times the input plus 1. Now we're asked to evaluate f of negative 2. So we'll say the negative 2 in place of the x, and then we simplify. This will be a negative 14 plus the 1 that hasn't been used. That gives me a negative 13. So f of negative 2 is negative 13. Again, here we're asked to solve f of x equals 36. Now x is not 36. X is what we're trying to solve for. Y, or f of x, is a 36. So we're going to take the f of x from the formula and completely replace it with the number 36 and write the rest of the formula. And our directive is to solve. We need to solve this. So we're solving for x. I'm going to subtract 1 from both sides and divide by 7. So I get x equals 5. X equals 5. Now, given the function f of x equals 2x squared plus 7x minus 7, let's calculate the following values. F of 0 is going to be 2 times, go ahead and write your function this way, put in the 0. So I have 0 squared is 0 times 2 is 0 plus 7 times 0 is 0 minus 7, negative 7. F of 2. Again, 2 times some input squared plus 7 times some input minus 7. So then I put my input of 2 and I get 2 squared is 4 times 2 is 8 plus 7 times 2 is 14 minus 7 equals 15. Now I have f of negative 2. So again, we'll write our template from the function. It's 2 times some input squared plus 7 times some input minus 7. And my input is negative 2. Then we simplify. Negative 2 squared is 4 times 2 is 8 plus 7 times negative 2 is negative 14 minus 7. So I have 8 minus 14 minus 7 is negative 13. Now I'm asked to find f of x plus 1. So just the same way as we've written here before with writing the function again but with parentheses instead of x, we're going to do that here. So f of x plus 1 is 2 times parentheses squared plus 7 times parentheses minus 7. And what goes in the parentheses? Your input of x plus 1. So we've got a bit of work to do here. I'm going to go ahead and square this binomial. Go ahead and distribute here. I have 2x squared plus 4x plus 2 plus 7x. I might as well cancel those out. So 2x squared plus 11x plus 2. Same over here. I'm going to go ahead and write my template out. And I'm going to put my input of negative x and simplify. Negative x squared is the same as positive x squared times 2 is 2x squared. 7 times negative x is negative 7x and minus 7. Now, given a function 7 plus 8x squared, let's calculate the following values. F of a. Again, we can write the function with parentheses in place of our input and then put the input of a inside. A squared is a squared times 8, so we get 7 plus 8a squared. f of a plus h. Again, we're going to write 7 plus 8 times a plus h, quantity squared. We need to square that binomial, so we'll keep the 8 out front and keep this in parentheses because when we're finished, we will have to distribute that 8. This is a squared plus 2ah plus h squared. This is 7 plus 8a squared plus 16ah plus 8h squared. The next, we're being asked to find f of a plus h minus f of a all over h. It seems like a big task, but you can see we've taken care of the parts above. F of a is up here, the 7 plus 8a squared, and my f of a plus h is in simplified form right here. Okay, so I'm going to go ahead and put those pieces in where they belong. Okay, and the bottom is just a plain h. It's not an f of h or anything. You just copy down h. So we'll put our green part that we figured out before in place of the f of a plus h. And then we're subtracting f of a. Now we have to be careful because f of a ended up being a binomial. So we need to make sure that we are subtracting both parts of that binomial. And then it's all over h. Okay. So let's go ahead and clean up what we can. I know that my 7 and negative 7 cancels. I have an 8a squared and a negative 8a squared that cancel each other out. And that leaves me with 16ah plus 8h squared on top, both being divided by h. And now we can see h is going to divide both of those. So that gives me a 16a plus 8h is how that function evaluates at the end. Now we can also give functions in verbal form. This is something that you're going to see a lot in calculus if you move on to the calculus sequence, and it's very useful. It's actually the basis of finding derivatives. So this is just an introduction to the algebra part of putting this together and cleaning it up at the end, but it is something that you're going to want to know. Don't just kind of brush this off as a one-time thing. It is very important, and we want to make sure that you get the practice on it now. All right, functions can also be given in verbal form. Here we have the population in thousands of people, P, of a certain town, given by P equals f of t. And T is the number of years since 2010. In 2017, the population was 63,000. They want us to express this information in terms of the function f. All right, so my function is named f. F of my t, well, in 2017, it is 7 years since 2010, so f of 7. My f of 7, in other words, the population at year 7 years after 2010 equals 63,000. So that is relaying that information in terms of a function f. Here, a rental car company charges $124 and an additional $38 rate per day. Want to write a formula using function notation that expresses the cost C as a function of the number of days D you rent the car. So this is going to be in place of the y, and we're doing this as a function of D. This is in place of x that we would normally use. Okay, let's try and make a t-table here. We have D and C, just to see if we can detect a pattern. Let's say that we rented the car for 1 day. 1 day. How much is that going to cost? That's going to cost us $38 and $124. $38 for the day and $124 for just renting that car at all. How about we rent it for 2 days? Well, the $38 is the daily rate, so now we're going to have to pay 2 of those $38 and the $124 just for renting the car. All right, how about 3 days? We're going to pay 3 of those $38 charges and the $124 again. Okay, so we can detect we have a pattern here. If we're going to rent the car for D number of days, this is where the day is going. You can even put 1 up here and see that as D is 1, this is 1. As D is 2, this is 2. As D is 3, this is 3. As D is D, this is going to be D times 38 plus 124. So we can see that the cost is going to be 38D. We'll just switch that around and make it a little nicer, put the coefficient in front, plus 124. One-to-one functions. Now, some functions have output values that correspond to exactly one input value, and this is called a one-to-one function. It's an even more specialized relation. If we look back at the schematic diagram from the first page of our notes, you can see this here. Let's see which of these relations are one-to-one functions. Okay, so this is where we have a function where all the output values correspond to exactly one input value. So we have an output, and does it go to exactly one input or come from exactly one input? And yes, we have an output here, and does it come from exactly one input? No, it does not. So this is not one-to-one. This output came from exactly one input. This output came from exactly one input. This output came from exactly one input. So this is a one-to-one function. Now this output here came from exactly one input. This output came from exactly one input, and this output came from exactly one input. So you might think that it's a one-to-one function, except if you look back in those notes, this was not even a function in the first place. So even though every output comes from exactly one input, it's not a function. For something to be a one-to-one function, it has to be a function in the first place. This one is not a function, so it can't be one-to-one. I usually say something like, I can't be your favorite aunt because I'm not your aunt. Okay, for me to be your favorite aunt, I would have to be in this set of being one of your aunts, and then I can have a chance of being your favorite aunt. So same with this. Even though every output came from exactly one input here, it was not a function to begin with. it's not a one-to-one function because it's not a function at all. So a general note, a one-to-one function is a function. Remember, it has to pass being the function. Every x has exactly one y, and every output value corresponds to exactly one input value. Okay? In other words, every y has exactly one x. All right, if you're given a graph of a function, you can determine if it's one-to-one using the horizontal line test. Okay, so horizontal line test here. Roll your pencil from top to bottom and see, does it hit more than one place? Here it does, so we're going to say that this is not one-to-one. Just like we did before, let's just make up some points here. Say this is -4, 1, and this is 1, 1, and this is 5, 1. You can clearly see that we have a y value of 1 that is being mapped to more than one value of x. So it doesn't pass the definition of being a one-to-one function. It is a function. It passes the vertical line test, but it is not a specialized function as a one-to-one function. Okay, let's see if we can pass a horizontal line test here. So here we go. Passes the horizontal line test, but be careful. This is not a one-to-one function. The reason is, you guessed it, it is not a function at all. It doesn't pass the vertical line test. So if it doesn't pass the vertical line test, then you're not going to see if it further passes the horizontal line test. So this is not even a function. It definitely can't be a specialized one-to-one function. Now let's see if we can do a horizontal line test here, and it's not working. We're not working here. We've got two places that it's hitting as we draw it through there. So this is not one-to-one. Okay. An example of something that is going to be a one-to-one function might be your cube root function, something like this. This is something that passes the vertical line test, also passes the horizontal line test. So this is one-to-one. All right, given an equation that represents a function, let's express it using function notation. Here is the relation x plus y cubed equals 13. Let's just get it into function form. In other words, f of x equals form. We have to solve for f of x. We have to solve for y. So we start out with this x plus y cubed equals 13. I'm going to subtract x from both sides so that I can isolate the term that I'm trying to solve for. Okay, this variable y cubed I can get by itself if I take the cube root, and I will have to do that to both sides. So y is the cube root of 13 minus x. We'll write it over here in our function notation. Cube root of 13 minus x is our f of x.